Hi, you are watching Satellite Communication Lecture Series, and today we are going to discuss about the digital transmission system. And digital signals are coded representation of information. For example, a baseband signal may consist of one or more information signal. For example, a number of telephone signals in digital form may be combined into one baseband signal by a process known as time division multiplexing. Analog signals may be converted into digital signal for transmission. Digital signals also originate in the form of computer and other data. So in general, a digital signal is coded version of the original data or analog signal. And now in this video, let us discuss about the characteristics of some more common types of digital baseband signals along with the representative methods of digital modulation. Keyboard characters, for example, are usually encoded in binary digital code. A binary code has two symbols, usually denoted as 0 or 1. For example, teleprinter code may use the combination 110000 to represent the letter A. Analog signals such as speech and video signals may be converted into digital form through an analog to digital converter. A particular form of A to D conversion is employed known as pulse code modulation, and some of the sources maybe you can use medium data rate PC, and you can also use an analog to digital converter or analog digital converter with a bit rate reduction, that is digitized video can also be used. In digital terminology, a binary symbol is known as a binit or from binary digit. The information carried by a binit is in most practical situation equal to unit of information known as bit. Thus, it has become common practice to refer to binary symbols as bits rather than binits, and this practice will be followed here. And the digital information is transmitted as a waveform, and some more of the waveforms used for binary encoding are shown in this diagram one by one. And now let us discuss about it one by one. And these will be referred as digital waveforms, although strictly speaking they are analog representation of the digital information being transmitted. For example, let us take a binary sequence called 10101111. Okay, and the duration of the bit is referred to as bit period or TB. The bit period is given by 1 by TB. With TB in seconds, the bit rate will be in bits per second. Okay, usually denoted by B by S. And this diagram shows the unipolar non-return to zero waveform, meaning that the waveform excursions from zero are always in the same direction, either positive or negative. They are shown as positive A because it has a DC component, and the unipolar waveform is unsuitable for use on telephone lines and radio links, including the satellite link. And the next diagram, what you see here is a polar waveform which utilizes the positive and negative polarities. In Europe, this is referred as bipolar waveform, but the term bipolar in North American usage is reserved for a specific waveform. And for a long and random sequence of ones and zeros, the DC component would average out to be 0. However, long sequences of like symbols result in a gradual drift in the DC levels, which creates problems at the receiver decoder. So, what you could do is, also the decoding process requires knowledge of bit timing, which is derived from the zero crossovers in the waveform, and these are obviously absent in the long strings of like symbols. Both unipolar and polar waveforms are known as a non-return to zero waveform, that is NRZ waveforms. This is so because the waveform doesn't return to zero baseline at any point during the bit period. And now let us see and return to zero waveform, that is polar return to zero waveform. So this diagram shows the example of polar return to zero. Here the waveform does return to zero baseline in the middle of the bit period. So transition will always occur even within a long string of like symbols, and bit timing can be extracted. However, DC drift still occurs with long strings of like symbols. In split phase or Manchester encoding, A transition between positive and negative levels occur in the middle of each bit, and this ensures that the transition will always be present so that bit timing can be extracted, and because each bit is divided equally between positive and negative levels and there is no DC component at all. Okay. A comparison of the frequency bandwidth required for digital waveforms can be obtained by considering the waveforms which alternate at the highest rate between the two extreme levels, and these will appear as this waveform in the square waveforms. For the basic polar non-return to zero waveform, this happens when the sequence is 10 10 10. The periodic time of such a square waveform is 2 TB and the fundamental frequency component is 1 by 2 TB. So, for the split phase encoding, the square waveform with the highest repetition frequency occurs with a long sequence of like symbols such as 1 1 1 1 1, and the periodic time of this square waveform is TB, and hence the fundamental frequency component is twice that of the basic polar non-return to zero. Thus, the split phase encoding requires twice the bandwidth compared with that basic polar non-return to zero, while the bitrate remains unchanged. The utilization of bandwidth measured in bits per second per hertz is therefore less efficient. An alternative mark inversion code, AMI code, is shown here. Here, the binary zeros are at the zero baseline and the binary ones alternate in polarity. In this way, the DC level is removed while bit timing can be extracted easily except when a long string of zeros occurs. Special techniques are available to counter this loss problem, and the highest pulse repetition frequency occurs with a long string of 1 1 1 1 1. So, the periodic time of which is 2 TB, the same as the waveform, and the AMA waveform is also referred as bipolar waveform in North America. So, bandwidth requirements may be reduced by utilizing the multi-level digital waveforms. So, this diagram shows the polar non-return to zero signal for the sequence 1 1 0 1 0 0 1 0. By arranging the bits in the groups of 2, 4 levels can be used. For example, these may be 1 1 as may be written as minus 3A, 1 0 as A, 0 1 as minus A, and 0 0 is minus 3A. So, this is referred to as quaternary encoding, and the waveform is shown, and the encoding is symmetrical about the zero axis. The spacing between the adjacent levels is being 2A. And each level represents a symbol, the duration of which is the symbol period. For the quaternary waveform, the symbol period is seen to be equal to the twice that of the period time, and the symbol rate is 1 by R symbol is equal to 1 by T symbol. The symbol rate is measured in units of bars, where 1 BD is the 1 symbol per second. The periodic time of square wave having the greatest symbol repetition frequency is 2 symbol, which is equal to 4 TB, and hence the bandwidth compared with the basic binary waveform is halved. And the bit rate remains unchanged, and hence the bandwidth utilization in terms of bits per second per hertz is doubled. In general, a waveform may have m levels where each symbol represents m bits, that is m is equal to log 2 of m, and the symbol period st symbol is equal to m into TB. And the symbol rate in terms of bit rate as R symbol is equal to RB by m. For satellite transmission, the encoded message must be modulated onto the microwave carrier. Before examining the modulation process, we describe the way in which the speech signals are converted into a digital format through pulse code modulation. So, let us move on to pulse code modulation. So, the information was assumed to be encoded into one of the digital forms, and speech and video appear naturally as analog signals, and these must be converted into digital form for transmission over a digital link. For example, the speech and video analog signals are shown converted to digital form through the use of A to D converters. The particular form of A to D conversion is known as the pulse code modulation. Commercially available integrated circuits known as PCM codecs, that is coder, decoder, are used to implement PCM. Here you can see the block diagram, basic block diagram of a pulse code modulator. And there are many modulation techniques which are classified according to the type of modulation employed. Of them all, digital modulation technique used is pulse code modulation. The signal is pulse code modulated to convert its analog information into binary sequence, ones and zeros. The output of PCM will resemble a binary sequence. Here you can see the example of PCM output with respect to instantaneous values of the sine waves. So here a sine wave is converted into pulse code modulated waveform. Instead of a pulse train, PCM produces a series of number of digits, and hence this process is called digital. Each one of these digits, though in binary code, represent the approximate amplitude of the signal sample at that instant. In pulse code modulation, the message signal is represented by a sequence of coded pulses, and the message signal is achieved by representing the signal in discrete form in both time and amplitude. So these are the basic elements of PCM. And the transmitter section of the pulse code modulator circuit consists of sampling, quantizing, and encoding, which are performed in the analog to digital converter section. The basic operation in the receiver sections are regeneration of impaired signals, decoding, and reconstruction of the quantized pulse train. And the first block is the low pass filter, and this filter eliminates the higher frequency components present in the input analog signal, which is greater than the highest frequency of the message signal, to avoid aliasing of the signal. And the next one is sampler. This is a technique which helps to collect the sample data at instantaneous values of the message signal so as to reconstruct the original signal. The sampling rate must be greater than twice that of the highest frequency component omega of the message signal in accordance with the sampling theorem. Quantizing is a process of reducing the excessive bits and confining the data. The sampled output, when given in quantizer, reduces the redundant bits and compresses the value. The encoder is nothing but the digitization of analog signals done by encoder. It designates each quantized level by a binary code, and the sampling done here is the sample and hold process. These three sections, that is the LPF, sampler, and quantizer, will act as an analog to digital converter. Encoding minimizes the bandwidth used, and the regenerative repeater section increases the signal strength. The output of this channel also has one regenerative repeater circuit to compensate the signal loss and reconstruct the signal, and also to increase the strength. And the decoder circuit decodes the pulse coded waveforms to reproduce the original signal, and this circuit acts as the demodulator. After the digital to analog conversion is done by the regenerative circuit and the decoder, a low pass filter is employed called the reconstruction filter to get back the original signal, and hence the pulse code modulator circuit digitizes the given analog signals and codes it and samples it, and then transmits it in analog form. This whole process is repeated in reverse pattern to obtain the original signal. Thank you.